Hey, Science 30s, and welcome to our final discussion on the electromagnetic energy unit. I'm going to be discussing topic 2.2 today, astronomy. Three topics that I'm going to be discussing in today's video. We're going to be discussing the birth and death of stars, how we can see these stars using various forms of telescopes, and once these telescopes have found the information up in the sky, how can we analyze the information from these telescopes using a process called spectrometry. So we're going to be discussing those today. So first of all, our star, our sun, is one of roughly 100 billion stars that are found in the Milky Way Galaxy, which is our galaxy, our neck of the woods, as you can see here in a visualization of what our galaxy might look like. The Milky Way is roughly one of 100 billion galaxies in the universe, in the known universe. And the universe is estimated right now to be roughly 46 billion light years across and is getting bigger every second. And again, just remember, we do measure distances in the universe in light years, which is essentially the amount of time it takes an electromagnetic wave or electromagnetic radiation, the distance it can travel in 1 year. And remember, it's traveling at a speed of 3.0 times 10 to the 8th meters per second. So massive, massive scales here that we're dealing with. In the universe. And a large part of that universe are stars, and stars like our sun that are basically, living out their lives, quote unquote, their lives, basically powering themselves using nuclear fusion reactions, essentially taking two atoms of hydrogen and fusing them together into one atom of helium. And that essentially creates the massive energy that is being produced by the sun. These reactions that are in the core of the sun basically is going to create large magnetic fields. And again, if you want to see some details about it, you can read about the specifics in the notes. But suffice to say, this is happening in the core of the sun. And as the energy leaves the core and moves toward the surface of the star, it's going to interact with charged particles that are in the star's interior. And depending on how much energy is lost by the photon in these interactions, once they reach the surface, they are going to be emitted as various forms of EMR, which we discussed in our last video, which would be everything from visible light to X-rays to gamma rays to UV rays to infrared, all the different types of EMR that we discussed in our last video on 2.1. And these interactions can actually cause the sun as well, because they're charged particles that are in the sun. They can also create large magnetic fields around the sun, and these will create things like solar flares, which can, as you might be familiar with, can cause troubles with communications on Earth. If we get hit by one of these solar flares, we can get hit by like a burst that can actually disrupt communications on the planet. So, but that's essentially where the EMRs are originating, and it's all originating from that reaction, that fusion reaction, the two hydrogens fusing into helium. So where do stars come from? Like our star, like the sun, where do they come from? Well, they form in regions of space known as nebula, or nebulae. Nebulae would be the plural of nebula. Nebulae are basically collections of interstellar matter, including interstellar dust, hydrogen gas, and basically they're just huge, kind of almost concentrated deposits of this material that are found in different regions of the universe. Gravity begins to act on these atoms and basically brings them toward one another, and basically you'll get eventually what's called a collapsing star or a collapsing cloud of material. If that material gets a high enough gravity and enough rotation, it will begin to actually, its mass will begin to increase, its temperature will begin to increase, and eventually you'll get what's called a protostar. Once that material hits a temperature of roughly 10 million degrees Celsius, that's essentially when the fusion reactions, the hydrogen fusion reactions kick in, and then that's basically when you get the release of EMR as your energy source, and that's when officially, hate to use the pun, a star is born. Go watch Lady Gaga and Brad Cooper now if you feel like you must after that horribly cheesy line. But that's how basically a star forms. Now, stars live out their lives in what is called the main sequence. So once they're formed, they live most of their lives out in the main sequence. And a couple of scientists in the early 20th century scientists by the name of Hertzsprung and Russell basically created one of the most famous diagrams in astronomy, and it's right down here. It's called the HR diagram. And the HR diagram basically plots out a correlation between the color of a star that you can observe through a telescope and the temperature of that star. So what they discovered through their analysis is they discovered that the hottest stars in the universe are the ones that are blue in color, and the ones that are coolest in temperature are red in color. And you can see here is sort of, the hotter stars are down on the blue side here, then they go down. The yellow stars, like our sun is a yellow star, they're sort of in the middle, and then the coolest red stars are down here. You'll also notice that on the top of the diagram, you've got a cluster of stars up there and a cluster of stars down here. Those stars are not what are considered to be main sequence stars. These are stars that are in the process of essentially shutting down or dying. So they're sort of in kind of a side groups that are not on the main sequence. They might be red but very large in size, or they might be very small but very hot or blue in color, depending on what stage of their their collapse or their shutdown that they're in. And I'll be discussing a few things about that here in a couple of minutes. So just be aware that that's sort of when you're looking at stars, it's sort of backward. You think of cool on a tap as being blue and hot being red. In stars, it's exactly the opposite. Blue are the hottest stars, and your red stars are your coolest stars. So depending on what type of star you're dealing with, and you can have three types of stars based on their mass. You can have what are called low mass stars, intermediate mass stars, or you can have high mass stars. Low mass stars are about the size of our sun. They're about 1.4 times the mass of our sun or smaller. Intermediate stars, mass stars, are going to be 1.4 to 8 times larger than our sun, mass-wise. And then anything that's bigger than 8 times the mass of our sun, is considered to be a high mass star. Now, depending on what the mass of the star is, they're going to go through different processes when they actually shut down and quote unquote they die. So low mass stars will initially, they will actually, as the hydrogen begins to run out, the core will contract and the outer layers will expand as the last of the fuel is used more quickly. So at that point, the star will actually get bigger, and it becomes what's called a red giant, which can be up to 1,000 to 10,000 times more brighter than the original star. So, for example, our sun, when it eventually runs out of hydrogen, will become much larger and much brighter. Even though it is red, it will be brighter because of its actual size, and so it's not necessarily going to be hotter, but it will be brighter because of the large size that it has. Once it expands outward, the outer layers are basically cast away from the star, and you actually get the formation of what's called a planetary nebula. Now, a planetary nebula, if you have enough of these nebulas in an area, they can essentially, that material can eventually be used later on to form new stars. So that's kind of a great recycling program that's going on in the universe. Stars die and they produce the nebula that then will eventually, hopefully, produce more stars in the future. Now at this point, the star is going to collapse in on itself. So after it expands initially to that large red giant, it's going to collapse down to what we call a white dwarf. And the white dwarf would have the mass comparable to a main sequence star, but it's only going to be about the size of the planet Earth. So you're looking at the sun, that the mass of the sun, being a mass of 99 point some percent of the mass of the solar system, essentially being shrunk down to the size of the Earth, but still having roughly the same mass that it did when it was that large star. It will become faint, even though it'll be kind of maybe white or blue in color. It's going to basically have kind of leftover heat that is basically emanating from that star, and that's why we call it the white star. Basically, at this point, no fusion reactions are occurring because all the hydrogen has been used up. We're looking at basically a glowing ember at this point. Imagine a glowing ember on a fire would be an example. It would be a good analogy to what a white dwarf is. And eventually, once all the heat disappears from that dying ember, it will become a black dwarf. Now, right now, black dwarfs are hypothetical. We've never actually seen a black dwarf in space, simply because we don't think the universe is old enough. It takes that long for these stars after they die. It takes it, imagine a star that's that much heat for so many billions of years takes a long time for that star to actually cool down. So we haven't actually witnessed black stars, but we theorize that the final stage of a low mass star's life cycle would be this what's called a black dwarf. When we go to intermediate or medium mass stars, things get a little different. We're still going to have an expansion out, but because that star is much larger than a low mass star, it's going to produce what's called a red supergiant, not just a red giant, but a red supergiant. An example of this would be Betelgeuse. If you know the constellation Orion, the belt of Orion, one of the stars in the belt is called Betelgeuse, and it actually is it's a super red giant right now that's in the process of, it will eventually begin to collapse at some point after the expansion. Now, when the red supergiant runs completely out of fuel, because all the hydrogen now is being completely spent from the red supergiant, it will actually explode. It won't produce a nebula. It will actually produce what's called a supernova. And these supernovas are basically are huge events. They can sometimes destroy the star in the process. There was actually a supernova that was basically that formed. The light of that supernova reached the Earth in roughly 1604, and it's known as the Kepler supernova. And there's remnants of the Kepler supernova even now. 400 years later, you can still see remnants of the Kepler supernova. That basically that light reached the Earth, and we're still looking at it for over 400 years. This explosion is sort of continuing on. If the star doesn't get destroyed in the supernova, it's going to then collapse in on itself, but even smaller than a white dwarf. It's going to produce what's called a neutron star, which can be as small as only 20 kilometers in diameter, which is extremely small. To put that in perspective, it's going to have a gravity about 2 billion times that of what we experience on Earth. A teaspoon of the star would be roughly 2 billion tons of mass. That's how much you would be able to fit. A teaspoon of that star would be that heavy. If some of them will actually spin and will emit radio waves from them, they will emit EMR radio waves. In some cases, they emit pulses, like I said, and then these forms of neutron stars have a special designation. They're called pulsars. So you may have heard of a pulsar. That's what a pulsar is. One of the young pulsars known is one in the Crab pulsar that was formed by a supernova that was observed on Earth at about 1054 AD. So that pulsar is roughly, it's not, from our perspective, it's 1,000 years old. But again, remember, that light would have traveled millions of light years to get to Earth. So that, what we see is essentially what's happened, millions of years in the past because of the great distances of space. We're not looking at real time when we're looking into the heavens. The further away an object is in the stars, the further back in time we're looking, which is kind of cool. So telescopes are kind of a time machine, which is kind of cool. The final type of star are the high mass stars. These are the ones that are 8 times or larger than the sun. These guys will undergo a very similar process to the intermediate mass stars. They're going to do a red supergiant first. They're going to go to the supernova, but because they have so much mass, when they collapse in on themselves, they don't form a neutron star. They make something even more cool. They create black holes, and black holes again have such a high gravitational field that EMRs can't even escape from. Light can't even escape from the black hole. And black holes, for the longest time, had not been observed. In 2019, we got our first photograph of an actual black hole from an observational telescope here on Earth. It's located in the galaxy M87, which is roughly 53.5 million light years away. And you can see the event horizon around it. There's some cool shots. This is the actual photograph there, and there's some diagrams to sort of illustrate what you're looking at there. But kind of cool. In order to get the image, the Event Horizon Telescope relied on a technique known as interferometry. I can never say it. Which is basically using a bunch of telescopes in like a chain sequence to basically increase the resolving power of the telescope. So it's almost like taking a bunch of computers together, tying them together to get higher processing power. Telescopes can do that as well. We can use multiple telescopes on Earth in a sequence. We can have multiple telescopes in like a small area, all pointed toward one object, and then we can actually increase the detail at which we're going to look at that object. I don't really have any videos per se in the YouTube video, but if you're interested in any of the thing I just discussed about the stars, I've got a ton of YouTube videos about white dwarfs, black dwarfs, supernovas, all that good stuff. What you might want to do is take a look at this video. I'll throw this one at you. This is about high mass stars and what they do and how they sort of collapse in on themselves at the end. That might be something kind of cool to look at. So, but again, there's a lot of other videos on my website that you might want to make access to. So if you're really interested in this whole star forming and collapsing on themselves thing, give those videos a look at my website. But again, I can only put 5 cards on any one of my YouTube videos, so I have to kind of choose wisely. So in that case, I didn't give you a lot of the links on that section of the notes. All right, so the next section of this video I'd like to discuss is essentially about telescopes. Now, telescopes have been around for about 400 years. They were invented in 1608 by a guy by the name of Lippershey over in Germany. He basically was working with lenses and basically discovered that if you put 2 lenses together in the right position to one another, you could actually magnify things that were extremely far away. And that became the basis for the telescope. I mean, Galileo was one of the first, scientists to kind of make the telescopes kind of popular and famous, but he did not invent them. It was Hans Lippershey who did that. And we've been using these telescopes to basically collect EMR information from space, the incoming EMRs coming from distant objects in space for 4 centuries now. And we do rely on several properties of EMR waves that to use with these telescopes. And some of these properties will affect which types of telescopes we can use and which ones are more effective. So I'd like to quickly go through some of these properties right now. EMR waves can do 4 things. They can do what's called refraction, reflection, polarization, and diffraction. And if you want to see the whole gambit before I discuss it, take a look at this video. It's going to discuss how light moves as a wave and what ramifications that has. As an electromagnetic wave, what are some of the things that it's going to basically be limited by, or what are some of the things that it's going to do when it encounters certain scenarios? But I'll quickly discuss them right now. So refraction, I mentioned a little bit last day in the video in 2.1. I said that if it enters an object or a medium that's thicker than air, like let's say water, or maybe I'm moving through glass, what it's going to do is it's going to actually slow down the speed of the EMR. So it's going to basically, it's going to bend. So refraction is essentially a fancy word for bending light. And earliest telescopes would use refraction techniques to basically bend light to basically, to show something that was far away. I'll get to it in a couple of seconds. Reflection, that's a pretty easy one. Reflection just means that if you get an EMR and it hits a surface that's hard, it's going to reflect off in an equal and opposite angle. That's basically, you pretty much know what reflection is. I mean, that's the basis for mirrors and all that good stuff. And there are, again, telescopes that use reflection. Pretty much all modern telescopes are reflecting telescopes rather than refracting telescopes, as I'll get to in a couple of seconds. There's another process which is called polarization, and you might have heard of polarizing lenses on sunglasses. Remember that EMRs are transverse waves. They have different angles of waves moving in at the same time. Well, when you polarize a wave, and it's very difficult for me to draw that on the board, but there's a great diagram here, or even if you Google it online. But polarizing an EMR is going to basically confine the vibration of that wave to single and one direction only. So you're not going to get a scattering of waves that can occur. So that's what a polarizing lens does in your sunglasses. And when you put them on, it kind of reduces the glare off the sun. And why it's doing that is any of the sunlight that's coming into your sunglasses are basically being reflected in only one angle. So you're reducing the glare off of other angles of the waves when they're coming in. So, and they do this by essentially creating slits. So if I've got a wave that's moving like this, and I got slits like this, well, that wave is going to hit that. It can't get around those barriers. But a wave that's doing this, it can sneak through that slit. So only this wave is going to get through. The wave that's doing this isn't going to be able to get through. So that's what a polarizing lens does. And there are great applications for that on day-to-day use. And the final one, which I'll be discussing as well today, is one called diffraction. Diffraction means that EMR waves, if they're coming in and they hit an edge of an object, they'll actually bend around edges of objects. So technically, if the light hits the edge of this little platform here, it's actually technically bending behind it. So the light's coming in this direction here toward it, and then it could actually bend this way or bend slightly this way. As you can see in the diagram, it almost like it's creating ripples around the bends of objects or the edges of objects. So diffraction we'll discuss the last topic of today's discussion, which will be about spectra. How do we analyze spectra, and how do we create spectra of our EMRs to basically analyze what data is coming in from our telescopes. All right, so let's quickly discuss what's going to happen here with our telescopes. There are two types of telescopes, generally speaking. We have what are called refracting telescopes, and we have reflecting telescopes. Refracting telescopes represent the earliest telescopes that were designed. They're the ones that use lenses. So they've got two lenses. They've got an objective lens. That's the one that's the big lens at the front of the telescope. And then you've got your smaller eyepiece lens at the back. Basically, the larger lens is used, the larger the lens that's used in the telescope, the less chance you're going to get diffraction around the edges of the telescope. So that you want bigger lenses to prevent the possible bending of light that's coming in. As well, larger lenses are going to give you what is called higher resolution. Resolution meaning how detailed the image is that's coming in. The more light I can let into my telescope, the higher the image quality is going to be when I see that detail of that image being enlarged in my telescope. There are limits to refracting telescopes, and that's why refracting telescopes are generally not used. You can still get refracting telescopes, you can buy them, but pretty much all the major telescopes that are used in the world today are not being used, are not refracting telescopes, is what I'm trying to say. The reason why is you are essentially limited to the size of your objective lens. And to make a lens bigger than 1 meter, you need to have perfect precision on how to make the lens. Like, you imagine trying to make a lens on your glass that's half the size of me. It's going to be very difficult to make it perfect and to make sure that everything is going to be smooth. And also the lenses just get too friggin' heavy. Like, you get a lens that's that big, they're going to become very cumbersome, very large, very tough to work with. So that's sort of the reason why refracting telescopes sort of kind of went by the wayside until Isaac Newton came up with his design. And Isaac Newton came up with the idea for the reflecting telescope. He came up with the reflecting telescope. Now, the reflecting telescope uses mirrors rather than lenses. And for this reason, they can become much larger. They can have larger openings to let even more light in, because mirrors are not as subject to restrictions in size as glass lenses are. In fact, a lot of modern telescopes now use segmented mirrors to create even larger diameters for these telescopes. And I'll get to a few examples of that here in a couple of minutes. But his design was revolutionary, and really we're still using reflecting telescopes to this day. They've sort of replaced the refracting telescope because of their immense power, because reflection on mirrors works way better than refracting or bending the light using lenses. Resolution of optical telescopes can be improved when two or more of them are put together, as I mentioned earlier. It's a process known as interferometry. I can never say it, but you're combining, you're daisy chaining telescopes together. And an example of this would be two massive telescopes that are found on the highest point of real estate in Hawaii, Mauna Kea, which is the top of the highest volcano on the Big Island of Hawaii. They have two telescopes that are called Keck 1 and Keck 2, and they have each of them has a 10-meter diameter segmented mirror. That's the size of their actual the mirrors that are reflecting the light from space, and they are literally 85 meters apart from one another. So these two telescopes can point at one object up in space, and their combined power can increase the resolution of the images that they're actually processing from space. An even bigger example of such a reflecting telescope is known as the ELT, which is the Extremely Large Telescope, which is going to be in the Atacama Desert in northern Chile. It's going to have a diameter of almost 40 meters with segmented mirrors, and it's going to be comprised of about 800 segmented mirrors that are going to be put together. But it will be pretty much almost, I think it will be the largest ground telescope in the world once it's done completion of its construction in roughly 2025. Many modern telescopes are designed to look at other types of EMR. So far, when we think of a telescope, we might think, well, it's capturing visible light. But a lot of telescopes out there do not, they don't look for visible, EMRs. They're not looking for what we see in our section of the visible light spectrum. They might be looking for X-rays or radio waves or microwaves. An example of this, as I just mentioned, are radio telescopes. Telescopes that are looking for radio waves that are coming from space, essentially. Now, they have an advantage. Because they're not looking at visible light, they can operate 24 hours a day. They can operate when it's sunny or cloudy. They're not looking for visible light coming, from outer space. So they don't have to operate only at night. They don't have to be. It doesn't have to be a clear night for them to work. So these telescopes can work like literally 24 hours a day, 365 days of the year to capture these radio waves that are coming from the most distant reaches of the galaxy. And they also have some of the because the radio waves have the longest electromagnetic waves of any of the electromagnetic spectrum, they have to be extremely large. And we're talking about some very large telescopes already, like 39 meters in diameter. That's nothing compared to some of these radio telescopes. The largest radio telescope in existence right now is actually built into the hillside, into a hillside in China, and it is roughly right now half a kilometer in diameter. So it's a 500-meter diameter parabolic bowl that's basically picking up these radio waves coming from outer space. And these radio telescopes, some of them aren't the biggest ones, but some of them have the biggest arrays in the world. Radio waves, these radio telescopes can be combined together to strengthen the signal of the radio waves that they're receiving. An example of this would be what's called the Very Large Array, as you can see here, which is found in New Mexico. It uses over 24 25-meter diameter telescopes arranged in a Y pattern on the ground, and they cover a distance of roughly 61 kilometers in the desert in New Mexico. This would be the equivalent of having a single refracting telescope or a reflecting telescope that has a single mirror with a diameter of roughly 27 kilometers in diameter. So by using multiple telescopes, we can certainly increase their resolution, whether they're picking up visible light on the electromagnetic spectrum, or whether they're picking up other types of electromagnetic radiation, in this case, obviously radio waves. If you want to be able to see clear, then on ground, you don't want to have it. Maybe you're worried about getting interference through the atmosphere. And that's always an issue. A lot of our telescopes are found in very clear locations that are high up, Mauna Kea, on tops of mountains, to eliminate the amount of the atmosphere that these light waves have to travel through in order to get a sharp image. Well, there's a simple way to avoid that. You put the telescopes in space, and you're probably familiar with, maybe at least one famous space telescope. You may have heard of Hubble, which has been up there for quite some time. It began its mission in 1990, and it's been basically looking at objects as far away as 13.4 billion light years away. That's how far into the sky that the Hubble has peered over the years. And it is one of many. There's actually several space telescopes that are in existence right now, and there are a few that are on the books here that are going to be coming out right away that are going to really revolutionize the way that we see the universe from our neck of the woods. Hubble, by the way, just to give a little bit of information about it, it has a primary mirror that's only 2.4 meters in diameter, and the telescope itself is roughly the length of a large school bus. That's how big this satellite telescope is. Due to the combination of its superior optics and the fact that there's no atmosphere, it basically it has the capability. The analogy would be it would be able to spot a nightlight on the surface of the moon from Earth. So if someone turned on a nightlight on the surface of the moon and we had Hubble down on the Earth, it should be able to pick up that night light clear as day by looking at it. That's a kind of resolutional power that Hubble has. But that's sort of a kick in the bucket. The next generation of space telescopes are already being designed. The next one is the JWST, or the James Webb Space Telescope. It is set to launch in 2021. There have been several delays on it, but it's going to have a segmented mirror that's going to make its diameter 3 times the size of that of Hubble. It's going to have a 6.5 meter diameter reflecting mirror that's going to basically bring the images into the telescope. And it's basically, it's going to be in a much higher orbit than Hubble as well. Hubble right now is about 550 kilometers above the Earth's surface. The JWST is going to be 1.5 million kilometers away from the Earth, so it's going to be in a much, much higher orbit, which is going to give it even less problems with any kind of atmospheric distortions, and we'll also be able to give us some pretty good looks back to Earth as well, I'm assuming. And it's going to mainly capture. It's going to be designed to capture mainly infrared. So its primary section of the electromagnetic spectrum that it's going to look at is going to be the infrared section. One more space telescope, which sort of combines space telescopes and our multi-wavelength telescopes that I've been discussing earlier. You've got the Chandra X-ray Observatory up in orbit as well. It's able to basically peer into the universe and looking for X-ray emissions, looking for these high energy sources in the universe, like black holes, like quasars, like supernovas. We're looking for these that are releasing these high energy bursts of X-rays, these bits of ionizing radiation that I discussed with you last time in section 2.1. Before we move on, take a look here. We'll do a little quick review on telescopes. It gives you everything you need to know about everything related to telescopes. So give that sucker a watch before we head on to our next section. And our next section is, in fact, our last section for today. Now that we've got all these telescopes that are bringing all this information into us, how do we analyze the EMRs that are being brought in, that are being seen or being observed by these telescopes? Well, what we can do is we can use the process of diffraction, which I talked about earlier, where you can actually you can basically bend light using very small grates or small sections. You can actually split the wavelengths apart into what's called in a process called diffraction grating. That is going to basically take, so for example, visible light. Let's use visible light as an example. It would take visible light, which is pretty much, we don't see it as multiple colors all at once. But if I use the process of diffraction grating, it's going to break it into what we call a spectrum. The rainbow of colors. We're going to be able to see our Roy G. Biv, as it were, right? Our 7 colors in the visible light spectrum. Then we can use, now that we've got the electromagnetic waves broken into a spectrum, we can use a spectrometer, which is a device which will actually analyze the specific wavelengths that we're seeing in the spectrum that's being produced by this diffraction grating. And there are several types of spectra that can be produced. You can produce either what's called a continuous spectra, you can produce a dark line or an absorption spectra, or you can produce what's called a bright line or an emissions spectra, which are all have a role to play, and I'll explain the difference between all of them right now. A continuous spectrum would be one that has all the colors from start to finish. So let's just use visible light as an example. I would see Roy G. Biv. I would see the whole spectrum from start to finish. This would be like if I was staring at the source, if I was directly beside the source of something that's emitting electromagnetic radiation. So if I was able to fly out to the sun and be a few thousand kilometers off the surface of the sun, and I could put a spectrometer there or diffraction grater there to basically split the EMRs coming off the surface of the sun, then I would get a continuous spectrum. The problem is we're not at the surface of the sun, nor would we want to be. So all of our observations are happening from Earth. Well, from Earth, there's going to be issues when we're seeing the light coming from the sun. And even more so if we're seeing the light from other suns or other stars that are in other parts of our galaxy, or even from distant galaxies from across the universe. If we're seeing the light coming from a distant galaxy, that light is passing through lots of gases that are found in the universe to get to where we are, to get to our telescopes on Earth. So what's going to happen is you're going to produce, in that case, potentially what's called a dark line spectrum. So what's going to happen is you're going to get certain parts of the spectrum that are going to basically go black, because as the spectrum, as that EMR passes through specific gases, the gases are going to trap certain parts of the electromagnetic spectrum, and it's going to hold on to them. Those parts of the spectrum will not get to Earth. So those missing parts of the spectrum will show up as little black lines, which indicate, the composition potentially of the gas that actually absorbed them. So this would be an example of what we call a dark line or absorption spectrum, and it's shown right here on the bottom of the page. If you have this slide up on your notes, this would be a great slide to have up right now, because the diagrams on the notes are way better than what I didn't draw any diagrams on the board because it wasn't going to happen. Very difficult to draw a spectrum on the board with 4 colored felt markers. The last spectrum that could show up is one called a bright line or an emission spectrum. These gases that now absorb these EMRs in the universe, if you, for example, heat them up, if they get excited, these gases, they will then all of a sudden emit these EMRs that they basically absorbed. And then at that point, we're going to see essentially the reverse spectrum that we saw for the bright line emission spectrum. We would see at that point a dark line, it would be opposite of the dark line emission spectrum. The dark line I'm blowing this out of the water. Take 2, let's try this again. If I have a bright line emission spectrum, which is basically coming from a hot gas that is now releasing the EMRs that it's absorbed, that bright line emission spectrum is going to be essentially an opposite spectrum to the dark line absorption spectrum. So rather than now seeing a large section of the spectrum with only little small gaps in the spectrum, now I'm only going to see very thin pieces of the spectrum with most of the spectrum blacked out. I'm only going to see the wavelengths that were absorbed by specific gases once they are releasing them. So they've initially absorbed them, but when we heat them up, maybe they're in a nebula, or there's maybe a supernova that blows those gases and excites them. Now they're going to release these EMRs they've been basically holding on to from the passage of EMRs from stars in the area or whatever. So those are the 3 types of spectrums or spectra that we're dealing with. Now, and here's a great diagram of them, by the way. This is a great slide here if you haven't seen it. Take a look at that one. It really does kind of show you the difference between a continuous spectrum, an absorption spectrum, or an emission spectrum. And now, but what do we use them for? What's the purpose? Well, what's the point of all of this? Well, here's the kicker. We can do tests on gases here on Earth. So I can see that helium or hydrogen or oxygen. If I run EMRs through these gases, each elemental gas is going to absorb, different parts of the electromagnetic spectrum. It's almost like a fingerprint for that element. So if I can see a spectrum that comes to Earth, and I can see that the light has, missing components, I can extrapolate based on that spectrum that I'm seeing from a distant star what the composition of the gases that EMR had to pass through to get to Earth. So I can make predictions of, hey, that light went through a nebula. Well, now I can see what the composition of that nebula is because of either whether it's absorbed some of the light or whether I'm seeing light that's being reflected off the nebula, whether it be a bright line emission spectrum. These can tell me the composition of objects in the universe that are essentially millions of light years away. So these spectrum are very important to allow us to make accurate assessments of composition of interstellar objects, whether they're stars or nebula or galaxies or whatever, right? And it can also do this for me as well. Spectra can also determine the direction of motion of objects that we're looking at. You may be familiar with the Big Bang Theory. The universe exploded and is in an expanding universe. Well, how do we figure out that the universe was expanding? How do we know that the universe was getting bigger? Well, we use spectra to do that. You may have heard of the Doppler effect. If a car is coming towards you, right, you'll hear that as it goes past you. You hear the higher pitch as it's coming towards you and the lower pitch as it's moving away from you. Well, why does that happen? Well, when a car is moving towards you, what it's doing is it's pushing the sound in front of it. It's compressing the sound waves in front of it, making those sound waves tighter, closer together, giving them a higher frequency, shortening their wavelengths. That's going to give me that higher pitch sound, right? Higher frequency. Higher frequency sounds have a higher pitch. As soon as the object passes me, on the backside of the object, the wavelengths have been sort of stretched out. They become longer. So they've actually become lower frequency, like lower sounds. So you hear that, like that. So that's the Doppler effect as it comes to audio waves. Stars work the same way. They don't produce sound waves. They produce electromagnetic waves. So how does this play out with a star? Well, if a star is moving toward us here on Earth, it would be compressing the electromagnetic waves in front of it, making them slightly shorter. Well, what's the shortest wavelength of light in the visible light spectrum? Well, the highest frequency wave in the visible light spectrum, it would be Roy G. Biv, would be on the violet or the blue end of the light spectrum. So we call that, if an object is moving toward the Earth, we would see a shift in the spectrum. Like you'd see the pattern in the spectrum, but it would be shifted. Like it'd be shifted over a little bit toward the blue side. So we would call that a blue shift in the spectrum. If an object is moving away from Earth, it's going to be extending the wavelengths coming out behind the star. So those lengths are getting longer. Well, what's my longest wavelength or my lowest frequency visible light wave? It's going to be Roy R red. So an object moving away from the Earth, you're going to see the spectrum shift. So if I were to see a pattern in a gas on Earth, I might see this pattern like that, like in the spectrum. Let's say I got this pattern here. Let's do this. There's my pattern right there, right? So let's say that this is my blue end, and this is my red end of the spectrum, right? So if an object from like a star is projecting that pattern because it's passing through that element or whatever, I would see it potentially shifting this way to the red side, or I might see that pattern shifting toward the blue side. The pattern is still going to be identical. It would be like, imagine if I took a fingerprint, but my fingerprint isn't here now, my fingerprint is somewhere else, somewhere along the line. And depending on where my fingerprint is, I can determine the pattern of my fingerprint is still the same. So I know whose fingerprint it is, but I now know whether the fingerprint is moving toward or away from the Earth, right? So based on whether it's a blue or a red shift. So what are scientists seeing with these shifts? Well, pretty much most objects that we see in the night sky are redshifted. Objects are moving away from the Earth. Until very recently, we really hadn't even seen a blue shifted galaxy. I think scientists saw their first blue shifted galaxy like back in 2019. There's only, I think, maybe one or two blue shifted galaxies that we've even spotted at this point, which means the galaxy is moving toward us. Pretty much every other galaxy out there is moving away. Well, what does that indicate? That indicates that the universe is expanding. That's how we came up with that theory that the universe is expanding, because every object or galaxy we're looking at has got this red shift when we look at it through our spectral analysis. Now, if you wanted to learn a little bit more about spectral analysis, watch this video. It does sort of clear up everything. It's about a 10-minute video, but it's definitely well worth a watch if you're still having trouble between understanding what a bright line or a dark line or an emission or an absorption spectrum are and where they're used and when they form and all that. Give that video a watch. That might make your life a little bit easier. That's our conversation. The unit's done. Hooray. We're on to one more unit after this. Will be Unit D. That'll be coming up right away. But until then, we've still got a couple of questions for you to do today. Got a quiz coming up, unit exam coming up. So here's the homework for this section. We've got questions 1 to 8, question 11, question 14, 15, 16, and 17, and questions 21 and 22 on pages 456 to 459 in the Science 30 textbook. That is it. We are now done. Electromagnetic Energy Unit, Unit C, is a wrap. Join me again next time when I start us off on Unit D, talking about sustainability, talking about our uses of energy here on the planet Earth. Until then, thanks for tuning in. Have yourselves a great day.